A circuit board manufacturer estimates the yearly demand to be 1 million. It costs $1,600 to set up the 3D printer for the circuit board, plus $10 for each one produced. If it costs the company $2 to store a circuit board for a year, how many should be produced at a time, and how many production runs will we need to minimize cost? So again, we're looking at minimizing the cost function. So when we talk about this, first thing we need to do is identify what our X needs to be. So our X needs to be the number of produced on each run, so the number of circuit boards produced on each run. The number of runs then is going to be the demand, which in this case is 1 million. So 1 million then divided by X. Okay, that's going to be the number of production runs. Now the cost function is going to come from the storage cost plus the production cost. Now the storage cost is it costs $2 to store the game for the circuit board for a year. On average, and this is always going to be the case, it'll be X over 2 units on hand. So 2 times then X over 2 is then just X. Now the cost then for each production run, okay, is it costs $10 for each circuit board to be produced. So that's going to be 10X, there's our variable cost, plus the $1,600 for setup fees for that production run. Now the total then production run cost for the year, I guess I should have written total there. That is going to be then the cost per production run, which is the 10X plus the 1,600. Times then how many production runs there are in a year. Well, there are 1 million divided by X production runs per year. So that's going to go then right there. Okay. And of course, multiplying this out, the numbers here are a little bit big. And of course, multiplying these out here, these numbers are a little bit big. Thank you, WebAssign. Plus then 1600. All right, so there's then that multiplication. And again, it's just a nice, simple distribution. Okay, from before, we said that our storage cost was, our total cost function was the storage cost plus the production cost. So the cost function then is my storage cost, which is then just X, plus then my total production run, my production cost. Boom, there we go. Okay. Again, we hear the word minimum, so we are automatically thinking we should go ahead and take that first derivative. This will be C prime of X is going to be 1 minus then, what is that, 1,600,000,000 X to the negative second power. And of course, we're going to go ahead, set that then equal to 0. Again, our maxes and mins can only occur at critical values, or critical values. Okay, so we're going to go ahead, we're going to solve this then for X, multiply then both sides by X squared. Taking then the square root of both sides, again, I recognize it would be plus or minus 40,000 technically. But remember, we can't produce a negative 40,000 circuit board, so it's just going to be then the positive result. And of course then, we want to go ahead and naturally we want to verify that this is in fact going to be a minimum value, because right now all we know is that it is a critical value. So we're going to take then the second derivative, and these numbers are huge. All right, and then that'll be X to the negative third power, which is then 32 lot here, over then X cubed. Now, plugging our critical value into our second derivative, these numbers are astronomically huge. So I'm not even going to bother computing them out. 3.2 billion, that's a positive. 40,000 to the third is positive. A positive divided by a positive is a positive, and all positive numbers are greater than 0. So, by the second derivative test, this is in fact going to be a min, which is awesome. Okay, so it asks, how many should be produced at a time? Well, that answer here then is the number produced on each run. That should be 40,000 circuit boards. The number then produced is 1 million divided by x. So in other words, 1 million divided then by 40,000. Well, 1 million divided by 40,000, that is 25. So this company is going to be producing 25 runs of 40,000 circuit boards. Okay, let's go ahead and talk a little bit about sustainable yield. Okay. Now, sustainable yield, we want to talk more so about what this means in terms of actual application. So, in Western Pennsylvania here, we talk a lot about deer, and the government issues deer hunting licenses to be able to go out and hunt these deer. Now, the way in which they determine how many licenses to release each year is based on the sustainable yield, okay? So we have a population size, let's call it P, and we're going to come up with some function, f of P, for example, which is going to be the size of the population next year. Okay, so the growth then of the population, okay, is the population size next year, f of P, minus then the population of this year's size. So let's say that this year our population is 300, and next year the population is 700. So the growth then would be 700 minus 300, which is 400. I close the window. I'm hoping you can't hear my neighbors with leaf blower behind me. Okay, so that's going to be then the sustainable yield. Okay, is bringing it back down to a more comfortable population size. So this is then how the government would determine how many deer licenses to release. Now, to find then the maximum sustainable yield, again, we hear the word maximum, so we automatically start thinking about taking the derivative. Now, I am going to emphasize here, I do these problems a little bit differently than the way your author does it. Either way is correct. I just like doing it the way I'm going to do it, only because it's more consistent with how we've done other problems. Marine ecologists estimate the reproductive curve for a swordfish in a fishing ground to be f of P equals then a negative 100th P squared plus 8P, where P and f of P are measured in hundreds. I want to find the population that gives the maximum sustainable yield and the size of that yield. Okay, so P then is our population size. Okay, and we are already given then our f of P. Okay, now to come up then with our sustainable yield function, that is going to be y of P equals then f of P minus P. So in other words, a negative 100th P squared plus 8P minus then the P value. I'm going to go ahead then. I am going to combine like terms to give me then a negative 100th P squared plus then 7P. Now we want to come up then with the maximum sustainable yield. So again, I'm going to go ahead. I'm going to take that derivative. In doing so then, I have negative 200th P plus then 7. As always, we're going to go ahead. We are going to then set this equal to 0. Solving for P, I'm going to add the 200th P over to the other side. Dividing then both sides by 200ths, I find that P then is equal to 350. Now, like we've done in all the other problems we've talked about in this section, as well as the last one, we're going to go ahead. We need to verify that this is, in fact, going to be a maximum. So we're going to take then that second derivative, plug our critical value of 350 into our equation, It's a nice constant function. This is less than 0, so by the second derivative test, of course then, it's going to be a max, which is exactly what we wanted. Okay, so the question then asks what the size of our population should be. Well, the size, as we said, that was equal to P, so our population size then should be 350. Now remember, this is then measured in hundreds of swordfish. It then asks what the size of the yield was. Now remember, the yield is the size of the population. So the size of the yield, that's going to be your Y of P. Okay. So as we said before, that's a negative 100th P squared plus then 7 times that 350. So the size of the yield then is 1,225. And again, that is in hundreds of swordfish. Okay, this is the last example then in section 3.5. So a conservation commission estimates the reproductive function for rainbow trout in a large lake to be f of p equals then 46 square roots p. Or we're going to rewrite that as 46p to the 1/2. Where p and f of p are in thousands, and p is then less than or equal to 1,000. Find the population that gives the maximum sustainable yield and the size of that yield. Okay? So as we take a look at this, first thing we want to do is come up with our sustainable yield function. As you recall, the sustainable yield function is f of p minus p. So when we substitute on in, then that's going to be 46p to the 1/2 power minus then that p. Now we're trying to get then the maximum sustainable yield. So we're going to take that derivative. Taking the derivative then, that's going to be 23p to the negative 1/2 power minus 1 equals then 0. In solving for p then, I'm going to add 1 over to the other side. And in the process, I'm going to flip that exponent. I'm then going to go ahead, I'm going to multiply both sides by p to the 1/2 power to get rid of that fraction. This then gives me that 23 equals p to the 1/2 power. We can then go ahead, we're going to square then both sides. In doing so then, this then gives me that p equals 529. Now, of course then, like we've done in the past, we need to go ahead and we need to verify. Now, as we take a look at this, we notice that we are on a closed interval from 0 to 1,000. That's what it means then up here when it says p is less than or equal to 1,000. We know we can't have a population size that is negative. Now we can't have a population size at 0. So we need to verify then from 0 to 1,000. So we can actually go ahead, make life wonderful, and use the first derivative test. Now remember the first derivative test, we plug in our endpoints of 0 and 1,000. We also plugged in our critical point of 529. To use the first derivative test, we plug these values into the sustainable yield function. All right, so at 0, the sustainable yield is 0. At 1,000, that is 554.65. And at 529, that comes out to be, ironically, well, I guess not ironically, but interestingly, 529. As you can then see here, this is in fact going to be our max, worst star ever. All right, so we verified it. So the question asks, find the size of the population. So my size, that is going to be 529, and that is in thousands, okay? Rainbow trout. And the maximum sustainable yield, as we found when we did the first derivative test, so that's y then of 529. So the size of my yield then is also going to be 529,000.